we got a ball, it's going to fall down, and then it's going to come in contact with the ground. But when it comes, so this is what it looks like, it's just falling. Right? When it hits the ground, it's going to squish a little bit, so it's going to sort of flatten out, sort of exaggerate that. All right, it's going to squish, and then it's going to unsquish and fly back up, but it's not going to go to quite the same height. We're going to lose a little bit. Just go to slightly lower height. All right. So we got something like this. We get falling. We've got it compressing against the ground. And then we get uncompressing. And then we've got shooting back up. Okay. So we've got phase 1, phase 2 is compressing, phase 3 is uncompressing, phase 4 is flying up in the air. These two phases are free fall. Okay. So we get two different free fall phases here. By the way, falling doesn't mean you're going down. All right. Falling means you're in the air without anything touching it. All right. So it's on the way down we're in free fall, on the way back up we're in free fall. All right. So we've got these two phases. Our ground is pushing against us. And so for these compression and decompression phases, that's where it's asking. All right. So release chest height 1.55 meters. Falls to the pavement, bounces back near the same height. When it is in contact with the pavement, the lower side of the ball is temporarily flat. Before this dent in the ball pops out, suppose that the maximum depth is 1.2 centimeters. All right. So it squishes down by 1.2 centimeters. So if you look at the difference in heights here, so we've got a 1.2 centimeter height difference when it's completely smushed. All right. So what's the maximum upward acceleration of the ball? Well, I would say that the upward acceleration, for simplification purposes, when we squish this ball down, we just stored a whole bunch of energy in that ball, right? And that's elastic energy. When we squish something, it's going to want to unsquish. And if things were perfect, if this is something we call perfectly elastic, this thing would bounce up to the same height that it actually started at. So we're going to assume, to make this simple, that the amount that it squishes down by, when it pops back up, it's going to pop back up in the same way that it squished. All right. So if we can figure out how much the deceleration of it squishing, that should be the same thing as the acceleration when it unsquishes, right, when it decompresses. So basically, we want to see when this ball falls down, it stops short in 1.2 centimeters. And the question is, can we figure out what that acceleration is over 1.2 centimeters? And how would we do that? So essentially, we've got a ball that's falling, and at this point, it's reached some sort of maximum speed, right? We've got some sort of velocity right here. Let's call that the initial velocity of the ball, just as it hits the ground. And that velocity is going to go down to 0, right, when it comes to a stop. And it comes to a stop over that distance. My delta x is 1.2 centimeters. So I know my final velocity is 0. I know my distance over which I stopped is 1.2 centimeters. If only I knew that, what equation could I use to solve this? What equation could I use to solve this? If I knew v0, v1, and delta x, we want to find, it asks us to find the acceleration. And we're going to find the acceleration of the ball as it stops. And we're going to assume if we reverse that acceleration when it decompresses, it should be the same. So if I'm going to find ax and I have delta x, v1, and v0, which equation would I use out of my set of equations? Did I see the equations? Which equation would I use here? Equation 8, right? But if you to use equation 8, I know that delta x is going to be 1.2 centimeters. I know delta x. Okay. I don't know the a. That's what we want to find. That's our big unknown 1.5. The final velocity of the ball is down at 0. We need to know what the initial velocity of the ball is. And that's the velocity just before it hits the ground. Only there's some way to figure that out, because then we be able to figure out the answer. So what are we going to do to figure that out? I need to know the velocity of the ball just before it hits the ground. Why did I just circle that? Yeah, we'll call this phase 1 here, all right? We're going to use phase 1. Let's use phase 1 to figure out the velocity of the ball just before it hits the ground. All right, so for phase 1, let's just draw a diagram for it. A y-axis in this case. Here's the ground down at 0. The ball starts up here, right? And it's going to come down to that point. So here we are at time 0. Down here, let me draw something. So we've got a ball here at time 0. We've got the ball down here at time 1. All right. So we're going to call this our y-axis. All right. And it told us that the ball, we call this 0 meters equals our final value for y. I'm going to call it y0. I'm going to call this and they told us how high is the ball to start with? 1.55 meters. Alright, so our y0 is 1.55 meters. So we're dropping 1.55 meters, and we need to find, for other part of the problem, we need to find the final velocity of the ball just before it's falling. Before it's dropped. Do you know anything about the situation? What's our initial velocity in the y direction? Initial velocity is 0 meters. We're dropping it, right? So it's going to start at 0. We need to find our final velocity in the y direction. All right. Do we know our initial height? We know our final height. That's good. Do we know anything else? What about the acceleration? We're going to assume it's gravity. Gravity in the negative direction. And that's our assumption. Alright, so we're assuming free fall here. So if we just set up a little table of initial conditions, we have y0 equals 1.55 meters, v1 equals 0 meters per second. Now, we got to use accurate numbers on here. We're not going to use rounded numbers on quizzes or tests here. That'll eat up all your error on WebAssign. And we know that y1 equals 0, and we want to find out what vy1 is. So what equation are you going to use to figure out what vy1 is, knowing all those things? What equation would you use to find a final velocity? Real quick. What's the easiest way to find a final velocity? Equation 8. So we have v final squared equals v initial squared plus 2a delta y. Okay. And so the nice thing is we know that's 0, right? That's negative 9.81. This is 1.55. Alright. So that we know that vy final is the square root of 2 times negative 9.81 times what? What's our delta y in this case? 1.55. Is it 1.55? Remember, delta y is y final minus y initial. Because if we put 1.55 in, we're going to take the square root of a negative number. All right. Our y final is 0, and our y initial is 1.55. That's where all the negative comes from. We cancel the negatives. So if you end up with a square root of negative, don't just get rid of the negative. Just go back and check your math, make sure you're not doing something that's wrong. So we get 2 times 9.81 negative times negative 1.55. When we work this out, So that gives the final velocity of the ball before, just as it's reaching the ground. Then we can use that. Two times 9.81 times 1.55. So we're at 5.515 meters per second. All right, and now we're right there. All right, so now we're going to go from here to squishing down to that height. So basically, we're going to move the distance we're traveling now is 1.2 centimeters. So this is phase 2 we're in now. And our initial velocity before we squished is that 5.515 meters per second. And now our final velocity when we reach this height is going to be 0 meters per second. All right. So this is how fast it's going to decelerate over this 1.2 centimeter, which is so our delta x is 0.012 meters. All right. So now we can run this equation, or delta y. So we're going to draw a y-axis for us to neaten this up a little bit. Basically, we've got our top of our ball. So really what we're looking at is the top of the ball. It starts out at 1.2 centimeters, and at the top of the ball ends at 0 centimeters being the top of the ball. So that's going to be 0.012 meter difference. All right. So we use equation 8 again because we need to find acceleration. We know initial final velocity and we know a change in position. So we have Bf squared equals Vy, Vf, the initial squared, plus 2 and now that's our unknown. We know that, we know that, we know that. You could use equations 5 and 6 and it would give you the time as well it takes to do this. I don't know if they ask for that. No, they only ask for the acceleration. You could use a 5 and 6 and it would give you the acceleration as well as the time, but we only need the acceleration, so I'm going to use equation 8. So I'm just going to solve this for AY. So I have BF squared minus BI squared all over 2 delta Y. That's going to give us our AY. So our B final squared is 0. The initial squared is 1 or 5.5 squared. In our we have 2, and our delta y is going to be negative 0.012 meters. And remember, this is negative because our final minus initial, our final is at 0 centimeters, our initial was 1.2 centimeters. So that's why this is negative. So our negatives do work out. Now we do is crank out the math. I'm going to take my last answer out of my calculator, square it, and then divide by 2, and then divide by 0.012. And I get 1267.25. So the 3 significant digits